and IC sine 240. This is very simple. Now from there, if any axis it is rotating, so let it is taking this, consider it is a D and this is Q. This is Q. This angle is 90. Entire axis is rotating. Rotor. Then, and this is the instantaneous angle. You see here I have mentioned. This is the instantaneous angle, which is always, as I told initially, the rotor is always lagged from the stator. So basically that is called the slip. So if in case of a synchronous machine, this line, it is perfectly here. Very small angle, delta, that is called the load angle. It will be not this much. So this is a very simple phasor vector diagram. Here splitted all the stator and the rotor current. It is splitted here. Here I have used the notation SD. What is SD? Stator D axis. This is the direct axis. SQ, stator quadrature axis. So this is the quadrature axis. This is the quadrature axis Q. RQ means rotor quadrature axis. RD is the rotor direct axis. Okay. So slightly I am going to the governing equation. Okay. So this is the stator, this is the stator direct axis governing equation. So simple, it is very simple if you see the equivalent circuit. So this part is the resistive part. It's a KVL, simple Kirchhoff's voltage law. And there is a rate of change of stator direct axis flux with respect to time, which is producing voltage. And omega, this is the synchronous speed as it is rotating. So this is coming from the quadrature part of the stator, but it is opposing in nature. So that's why VSD is this one. So from here, we can tell the voltage, the rotational voltage, which is getting produced from this equation. It is only this, because omega is involved. So I given the name, the rotational voltage developed in the stator direct axis is this one. Similarly, in quadrature axis, the equation is this, but it's not opposing. If you see that vector diagram or equivalent circuit, you will understand that. You can refer any standard book like B.L. Thereja, A.K. Sahani, any book you can see. It will be very clear. This equation is a Kirchhoff's voltage law in a loop, and the signs are based on the polarity. You can very easily understand. So in quadrature axis, similarly, the rotational voltage is this one. So this is your rotational voltage. Now the rotational power, you know, power is equal to voltage into current. So total power, rotational power, that means the power is involved for the rotation. This is this one. Stator direct axis rotational voltage into stator direct axis current and the quadrature part. Okay. Now you see here I am putting the value of the I am expanding it. Already we know we have from the previous equation we know VSD rotational is equal to omega s into psi sq. Similarly, same thing I have put here. And this psi SD, that means the flux, the stator direct axis flux, which is very simple. LSS into ISD. What is LSS? LSS is the total inductance. It is leakage plus mutual. Okay, and mutual part is coming from the rotor side, so that's why IRD. Similarly, psi SQ, that means the stator quadrature axis flux, is equal to total inductance, stator inductance into ISQ plus mutual part is coming from the rotor quadrature axis. Now, if you substitute this psi SD and psi SQ in this equation, it is coming something like this. Something it will be cancelled out. Okay. So here you see the two terms are there. One is IRD and another is IRQ. Now it is very difficult because the rotor is rotating. So there is no measurement at the rotor side. So to implement physically, practically, you have to eliminate that. There I can't put any measurement. I don't have any access. Direct access I don't have. I have to eliminate it. So I'm in the next what we will do, we will try to substitute it. So here similarly the rotor flux, direct axis flux is equal to total rotor inductance, which is also leakage plus mutual into direct axis, rotor direct axis current plus mutual into stator direct axis, which is induced from the stator side. So as I told, I want to replace the IRD. So simply it is coming like this. And similarly, I want to replace the IRQ also. So it is coming like this. Now, in the previous equation, in place of IRD, I am putting this. And in place of IRQ, I am putting this. Now, I am simplifying it. After simplifying, it is coming like this. So the total rotational power is equal to Lm into omega s by Lrr into psi Rd into Isq minus psi Rq into Ist. Now we know power is basically what? Power is basically torque into RPM. Torque into RPM. That is the mechanical RPM. Okay. So in order to get the mechanical speed, the synchronous speed will be divided by P by 2. Okay. Because it's you know, this very simple formula, simple conception. So synchronous speed, when it is going to the mechanical side, rotor side, you have to divide by simply pole by 2. So that's why in place of this, I am putting this and divided by pole by 2. Now, if you this side it is cancelled and it is coming like this. This is the torque equation. It is coming like this. So this is cancelled So this is coming like this. But you remember this 3-phase, it is converted to 2-phase. And all we are doing all the calculation so far. Now, if we want to do the power balance, then we need to multiply these things by 3/2. So for an induction machine, asynchronous 3-phase induction machine, the torque equation is like this. Exact torque equation is 3/2 into P/2 into Lm by Lr into psi rd into Isq minus psi rq into Ist. So now, you know, all these things are passive parameter, which I can take as a constant. Now, what I told initially, to implement the vector control, you have to make one analogy of separately excited DC machine, which can be applicable to induction machine. So I am trying to convert all the governing equation of an induction machine, which can be identical, which having some identity with the governing equation of separately excited DC machine. You can remember the torque equation of a separately excited DC machine is some constant into some flux into armature current. Now, this entire part is a constant, this is a flux, and this is the armature current. Now, if I make the psi rq 0 by somehow, then I will get the equivalent torque analogy of an induction machine, same as separately excited DC machine. So basically, I am trying to do that. If what I'll, because your from your department, if some students they are attending the seminar, I would like to request at least 1 or 2 people, you will implement it. I will help you later on. Some student from regularly they are coming. Lot of student, I forgot their name. One I can remember one boy. His name is Aditya. He's my one of the, I can tell, one of the bright flame. He implemented in my lab that vector control with the test inverter. So at least I will expect 1 or 2 students, if students are attending the seminar, they can implement it. It's a very interesting thing. So what I was telling, now I have to make the psi rq to 0. I have to make the psi rq to 0. Now, if you say this is the direct axis and this is the quadrature axis, and your rotor flux is somewhere here, psi r, and this is your theta. It is instantaneous. The rotor angle, it is rotating. Now, this is your psi rq, and this is your psi rd. Sorry, this is your psi rq, and this is your psi rd. Now, if I bring that, somehow I reduce the angle. Now the psi r is coming here. So now psi rq is reduced. Further, I am bringing here psi rq again reduced. And if I align the psi rq with d axis, sorry, psi r, if I align perfectly psi r with the d axis, then my psi rq is 0. And the total flux is nothing but the direct axis flux. So to make the torque analogy, I need psi rq to be 0, as I told in the earlier equation. Here, you see, here I need this is to be made 0. So this is to be made. If I need to make it 0, what is to be done? I have to align the rotor flux with the d axis. Now I am concluding after this discussion, this maybe 45 minutes of discussion. Now I am concluding few things. One is to implement the vector control on induction machine, I need to create a analogy of separately excited DC machine. To do so, first I am taking the torque equation. In separately excited DC machine, the torque equation basically is the product of flux and armature current. But we obtained the torque equation in two phase, in two axes. Why two axis? I will tell you, because three axis control it will be difficult physically. So that's why we are converting to two axis. That is the summation of two component, two flux. So if I want to eliminate one flux, then it will be identical to the torque equation of a separately excited DC machine. That means in the induction machine, the quadrature axis flux I need to minimize it to 0, which is nothing but to align the instantaneous rotor flux with the direct axis of synchronous rotating reference frame. So now the main technical statement behind the vector control or field oriented control of induction machine is to align instantaneous rotor flux with the direct axis of synchronous rotating reference frame. Again, I am repeating. To implement the vector control for an asynchronous induction machine, the things which is to be done, the control which is to be implemented is nothing but to align the instantaneous rotor flux with the direct axis of synchronous axis, direct axis of synchronous rotating reference frame. Now I am coming slightly to the implementation. I'll not go in depth of that because today our target is to apply of machine learning. So that I will concentrate. So this is your direct axis. So here I have to set the reference flux, which is given by the machine manufacturer. And this ISD, which will be coming from another block, another computational block, where we are taking the three-phase current and converting to two-phase current. As I told earlier, the Park and Clark transform. So from there, the ISD, it is getting compared and error signal is generating, which is going through a compensator. And it is producing the direct axis voltage of the stator. So the direct axis loop of this control is very easy, and naturally it will be very stable. Flux loop of vector control is more or less very stable because it is very simple. But this compensator, how to tune that compensator, that is another never-ending topic. One day I will tell you some simple technique how to tune that, because the entire in this control there will be total three compensator PI regulator. Why PI? Because it's a second, it's a first order system. PID is second order. So it will unnecessarily, the higher order effect will come to increase the transient. So, and PI regulator implementation also, it is much more easier. So that's why most of the industry, they will use PI, where the fast response are, where the, not fast, where the robust response, dynamic response are required. Okay. So now I am coming to that, because as I told, the rotor is rotating by its mechanical, maintaining the mechanical speed. But where is the rotor flux? That position identification is very, very important, because you remember in the Clark and Park transform, they need a theta. That theta is basically the instantaneous angle, of the rotor flux. That is very, very important. It is to be needed. Otherwise, the entire control is become unstable. So now this is the rotor direct axis voltage equation as the stator. So this is the due to resistance, and this is the change of flux. And this part omega s minus omega r, why I have told, because this is the relative speed, and that due to that relative speed only the flux will got cut and produce voltage. So that's why it is given synchronous speed minus the rotor mechanical speed. But you know, in induction machine, the rotors are short circuited at the both end by short circuit rings. So that's why rotor bars are shorted. If it is shorted, so this voltage will be 0, left hand side. And for vector control, what we did? This made 0 because it is to be aligned. So for what I have told. So this equation converted to this equation. Now this rotor direct axis flux, because there is no quadrature axis flux. So basically that is coming now, no quadrature. When I am implementing the vector control, there will be no quadrature. Entire flux is the total flux, which is getting by the magnetization current. So that's why I am writing, and it is coming from the mutual part, because there is no electrical connection. There is a air gap. So that's why I am writing mutual into magnetizing current. We know psi RD already, we know the equation, what is psi RD. And now you got after vector control, when you are implementing, it is this one. And from there, as I told, the IRD, the rotor side implementation, rotor side measurement is not available. So I am replacing that. So in place of, sorry, this will be IRD, it is not L. This IRD, it is replaced by this value. Now the differential equation, finally it is turned like this.